All right, let's look at the definition of the inverse of a matrix. First thing to notice here is that this only applies to square matrices. If it's not square, we do not call it invertible. So square meaning like the number of rows equals a number of columns, sort of like this matrix here or this matrix here, 3 by 3 squares, or this 2 by 2 matrix here. So it's invertible if there exists another C by C matrix that we call A inverse, or the inverse of A, and that matrix A inverse has to have these properties. A times A inverse has to give you I. Sort of like we could say that 5 inverse is 0.2 because that means 0.2 times 5 equals 5 times 0.2 equals 1. And the number 1 works kind of like the identity matrix. I guess technically it is the 1 by 1 identity matrix. Anyways, let's look at this blurb here. It turns out if there are two matrices, P and Q, each satisfying this definition of the inverse of A, meaning like P times A times P equals I, and Q times A equals AQ equals I. So if those things are true, then P is the same thing as P times I. Multiplying a matrix by the identity does not change it. I just realized I'm not sure if the previous section went over multiplying by the identity matrix. So what we're going to do really quick is on a spare bit of paper here, let's just multiply a matrix by the identity to see what you get. So just using the row column rule, you can see that any old 3 by 3 matrix A times I3 gives you A. And if you do I3 times A, whatever your columns of A are, the definition of this is I times the one column and I times the second column of A, and so on. And we talked about in 2.1 that this matrix, when you multiply it by any vector, doesn't change it. All right, so that's a little blurb on why the identity matrix times any matrix is itself, either way that you do it. Okay, so yeah, get back to this. So yeah, you can see P is the same as P times I, and because we have that Q is an inverse of A, we can replace that I with AQ, and then we have a associative rule for moving parentheses around. So you can move the parentheses around here. And we also assumed that P is the inverse of A, which means P times A is also going to be I, and the result is Q. So if there are two matrices P and Q that are the inverse of A, then they're actually the same matrix. P is equal to Q, so the inverse is unique. So that's why we have like the symbol A inverse, because for any given A inverse is just one matrix. All right, let's look at example 1 here. We've got these two matrices E and F. These are not very different from the identity matrix. The only difference is that 4 and negative 4. Now, we want to show that E is equal to F inverse. So what it means to be the inverse of f, well, it means we should be able to do E times F and get the same thing as F times E, and that should be the identity. So E should be the matrix that you can do this with. Likewise, for F to be the inverse of E means we can do F times E. We should get the same thing as E times F, and that should be the identity. Now, you might be able to see that these are really the same thing, so this is kind of a argument that E equals F inverse if and only if F equals E inverse. Okay. So anyways, let's multiply it out and see what happens. Let's think about the first row of this result. So for the first entry here, we're going to be using row 1 of E and column 1 of F. And you can see that the only place there's a non-zero number in this row is the first thing. So the 0 and the -4 don't matter. So you just get 1 here. In row 1, column 2, this 1 gets multiplied by the 0, and this other 1 over here gets multiplied by this 0. So when the rows and columns don't line up, like row number 1 and column number 2, and we're talking about identity matrix columns, you're always going to get 0 here. And the same thing happens over here. These are a row of the identity matrix in row 1 doesn't match up with column 3. All the 0 things get multiplied by non-zero things, and you just get 0. And a similar thing is going to happen will happen in row 2 of EF. So if we're in row 2, column 2, then you do 0 times 0, 1 times 1. Hey, that lines up, that gives you 1. But in the other columns, all of the zeros line up with non-zeros, and that becomes that. Now, an interesting thing is going to happen in row 3 of this. Let's actually work it out. So in this position here, we're going to be doing the dot product of this 4, 0, 1 with this 1, 0, -4. Which is 0. In the second entry of this, we're doing the dot product of 4, 0, 1 with 0, 1, 0 now, which is 0. And in the third column, we're doing the same thing with the 0, 0, 1, and that gives you 1. So yeah, this is the identity matrix. But as a preview of some stuff we're going to do mostly in the next section, I want to point out something interesting about how this last row came about. What I want to do is see, like, what exactly are we doing with the 4, 0, and 1 from over here? Like, for example, let's group all of the terms that have a 4 in them, and I want to factor that out. Now, if we take this matrix, this 4, 0, 0 matrix, and add it to this other pair of matrices, we're sort of making like a linear combination of rows, essentially. So all the 1s are getting multiplied by the row -4, 0, 1. What I want to point out is that these 1, 0, 0 and 0, 1, 0 and -4, 0, 1 are the rows of F. And the way we're calculating this bottom thing here is by doing the corresponding linear combination of those rows using the bottom row of E as weights. Interesting. It turns out that works in general, and this is another way you can look at matrix multiplication. Matrix multiplication is deep, and there's a lot of different ways you can make stuff work. But anyways, you get the identity matrix. We also should be checking that F times E is the identity matrix. Let's do that really quick. So yeah, you get the identity matrix either way. So we can conclude that F is E inverse and E is F inverse. So yeah, let's look at example 2. Let's explain why this matrix A is not invertible. So we want to explain why this matrix A is not invertible. Whatever the inverse is, maybe it's B. Let's just say that if B is any 2 by 2 matrix, then B times A is by definition B times this vector 6, 7 as the first column, and B times the vector 0, 0 as the second column. And that, whatever the first column is, has a second column that is 0. And so that is not equal to the identity matrix that has a 1 in that position. So there's no way B times A can be the identity matrix. So it is not invertible. All right, let's look at example 3. This example is going to be another one that it's going to be a little involved, and it's going to justify theorem 2.10. Now, we don't have any way to find A inverse yet. We haven't seen any method for finding the inverse of an arbitrary matrix like this. But there's a trick. And to figure out the trick, let's think about what A inverse is. What is the goal? The goal is to find an A inverse. Let's say it has columns x1, x2, and x3. The goal should be that if we do A times A inverse, we should get the identity matrix. And remember, the columns of the identity matrix are E1, E2, and E3, so we're going to write it like that. And also, doing A times A inverse here, using the definition of matrix multiplication, is the matrix whose columns are A times x1, A times x2, and A times x3. So maybe you see where this is going if you just did this exercise 2 warm-up recently, that what we want essentially to get this inverse is 3 matrices that you can multiply by A to get the corresponding columns of the identity matrix. So essentially we want to solve 3 systems of linear equations. Like so. And to do that, we would row reduce these augmented matrices to, well, what's the goal when you're trying to like find the solution of something like this? And by the way, we know each one of these must have a unique solution because we showed before that the inverse of A is unique. So if A is invertible, if A inverse exists, there's a unique x1, x2, and x3 here. And what does it look like when you row reduce a matrix that shows you a unique solution? It's like what we had here, right? Every column needs to have a pivot, and you can't have two pivots in the same column because every leading entry must be to the right of the one above. So you're going to have every row with a pivot too. And the only reduced echelon matrix that has a pivot in every row and column is the identity. So the goal is going to be to get this to be row reduced to the identity matrix. But, excuse me, I wrote E1 there, but that should be the solution. Because, again, like we saw here, when we row reduced this augmented matrix, you end up getting the identity matrix here, which tells you basically x1 equals something and x2 equals something, and that gives you your solution to the equation ax1 equals e1. So same idea here. Now, do we need to row reduce all three of these matrices? Like, whatever row operations you do to reduce A to the identity, we're just going to have to repeat the process 2 more times in these other things. So that's going to be a pain in the butt. So let's save some work by doing all 3 at the same time. We're going to take A, augment it with E1 and E2 and E3, and this is going to represent all 3 of these equations at once. Okay. So let's actually do it. And on the other side, we just have the identity matrix. Okay, so let's do some row operations here. We can clear away this -1 by adding row 1 to row 2 and replacing row 2 with that result. Rows 1 and 3 are left alone. Then we can clear away this 1 by adding row 2 to row 3 and replacing row 3 with that, of course. Then let's scale row 2 by -1. Then let's clear out this 3 by doing -3 row 2 plus row 1 to replace row 1. Then we can do 2 times row 3 plus row 2 to replace row 2, and -10 times row 3 plus row 1 to replace row 1. And there we go. This has shown that A is row equivalent to the identity matrix. That means AX equals E1 has a unique solution, AX equals E2 has a unique solution, and AX equals E3 has a unique solution. So this gives us the x1 vector has the first component equal to -6, the second component equal to 1, and the third one also equal to 1. Same idea with x2 and x3. And yeah, this means that if we do A times this matrix that has these columns, you will get the identity matrix. Now we should also check it works the other way, that if we take this matrix and multiply it by A, do we get the identity? Let's just work it out super quick. Yeah, it does work out. Okay. Sounds good. So this example is an example of what theorem 2.10 says, that if A is a C by C invertible matrix, then this big augmented matrix, augmented with the whole identity matrix there, that is row equivalent to the identity matrix augmented with A inverse. That's what we did here. We started with A augmented with I, and we row reduced it to the identity matrix on the left, and that gives you the 3 columns of the inverse, like we just saw. Actually, I didn't really write the answer here clearly, but yeah, we found that A inverse is this. Okay, and the proof in the textbook is pretty similar to the example we just did. Let's do another example of just using this without going through the whole explanation, just saying we're using theorem 2.10. What the theorem says is that if this matrix A is invertible, in other words, if A inverse exists, then this augmented matrix here is row equivalent to the identity matrix augmented with A inverse. So let's see what happens if we row reduce this. Well, we want to get rid of this -2 here to get this to reduced echelon form. And so we're going to do row 1 multiplied by 2, add that to row 2 to replace row 2. And what you get is 0, 0. And the A part of this is already in reduced echelon form. And it's equivalent to A. And A is only equivalent to 1 reduced row echelon matrix, and it's this one, and so it's not the identity matrix. So A cannot be reduced to the identity matrix. So in other words, this statement here, that this augmented matrix is row equivalent to this other augmented matrix, is not true. And if that's not true, then A inverse doesn't exist, because if A inverse did exist, that would be true. So if a matrix is not row equivalent to the identity matrix, then that means that A is not invertible. And that's my justification for this corollary here. This little Venn diagram might look familiar if you read the proof writing section. So in this case, just to illustrate here, the if P then Q of that theorem we just saw is if A is invertible, then these matrices are row equivalent is the Q. Now, another way to say this is the contrapositive, which is if A is not row equivalent to I, that means not Q. Like if you're out here, if Q is false, then A is not invertible, meaning you're also outside of P. Now, in the next section, we're going to prove that the converse of this is actually true. That if A is row equivalent to I, then A is invertible. And it's really an if and only if thing. But we'll get to that later. Okay, this is me from the future here to tell you that let's take a break right now because I accidentally just recorded a really long video. And here's a good place to insert a break. See you in the next one.